Hi everyone, greetings of the day. This is Lekha here. I'm pursuing my master's in artificial intelligence right now. I, along with my teammate Manish, are going to present our final project for the course Pattern Recognition and Neural Networks. Our project title is Emotion Based Music Recommendation System. In this project, we combine computer vision, deep learning, and web technology to recommend music in real time based on users' facial expressions. So let's move on to the introduction. Uh, we are bridging the emotion and music part. So, music plays a powerful role in human emotions. It can uplift us, calm us, or reflect how we feel internally. Our goal was to build a system that understands this emotional connection and uses AI to detect emotions in real time, allowing music recommendations to adapt dynamically to the user's current mood. The problem was, our problem statement was most existing music recommendation systems rely on past listening history, genres, or collaborative filtering. While effective, they ignore an important factor: how the user feels at the current moment. This leads to recommendations that may not align with the user's emotional state. So, our solution is we designed a system that integrates real time facial recognition, facial emotion recognition with the music recommendation engine. We use efficient net models enhanced with CBAM, attention mechanism, to accurately classify the emotions and map them to suitable music recommendations. So, the power of emotional connection. Music has a strong emotional impact. As I said earlier, it can soothe stress, boost energy, or provide comfort. By incorporating emotion recognition, we can enhance the user experience and enable the application in mental health support, therapy, or human computer interaction. The literature review, which we went through for our project. These are the key research contributions in this area. We are using the efficient net, which introduces a scalable CNN architecture with high efficiency in emotional facial recognition. And we use CBAM, which improves the feature learning using channel and spatial attention. The dataset we used is FER 2013, which is a benchmark dataset for facial emotional recognition. And the music and emotion deep learning integration is one of the prior research which demonstrated the feasibility of emotion-based music recommendation. However, there are some of the some research gaps which we identified, and these three major gaps are limited real-time emotion music mapping, high computation cost on resource constrained devices, underutilization of attention mechanism. So our system, we are trying to address all these gaps. A system overview, how we detect from the facial recognition to soundtrack. So this is the flow chart which we have. Like once you start the application, it initializes the camera and our system, and it detects the face. Through face, it detects the emotion. We use the pre-trained model to detect the emotion and get the music recommendation system. So we have a music recommendation with few listed songs for each emotion. We have around 7 emotions, and all this data will be real time updated using our web app. And if you still want to continue, it will continue recognizing in live. We have a live video through which it detects the facial emotions and recommends songs based on it. Next, let's the technical foundations or the technical resources which we are using are we used a TensorFlow and Keras for a model development. We developed our web application for the facial recognition and music recommendation system using a Flask. And the core models which we used are EfficientNet B0 with CBAM attention mechanism and EfficientNet B3, both trained on FER 2013 dataset. For EfficientNet B3, we also use some dataset augmentation techniques to improve the accuracy. And coming to the system architecture, the emotion recognition module uses hard cascades for face detection and the efficient net CBAM model to classify detected emotion into one of the seven categories like happy, sad, anger, fear, distress, neutral, etc. And the music recommendation engine maps emotions to the curated playlists and outputs recommendation instantly. So this is the flow diagram for our emotion recognition module at the top, and here we have our music mapping. So we have a database, and we also have a mapping between for example, for happy emotion, these are the list of songs. So that mapping we have set it, and let's move on to the model architecture. We are using the efficient net 0 and CBAM architecture. So efficient net is a scalable feature extraction model. It is a lightweight. Efficient net 0, B0 is lightweight with about 4.4 million parameters. It offers fast inference and is suitable for real-time applications. EfficientNet B3 is a deeper model with about 12.2 million parameters. It provides higher accuracy but requires more computation. The CBAM is the convolutional block attention mechanism module. So this is like a general architecture of how the convolution block attention module looks like. It has a channel attention module and spatial attention module. So as presented here, like attention determines what is meaningful in the impact, whereas spatial attention pinpoints to where part of the information in the feature map. Uh, so the training for robust performance, what are the ways we have tried to improve the performance? We use the data set FER, which is like a very good data set for facial recognition currently present, and it's like state of art currently. And this is the we trained on the FER data set having 35,887 facial images. They're categorized into these seven emotions: angry, disgust, fear, happy, neutral, sad, and surprised. We applied data augmentation methods to enhance the model and also to prevent overfitting. The different data augmentation we applied are random flips, rotations, and color jitter to create a difference in the data training samples. And the optimizer which we used is Adam W optimizer and for its effective regularization techniques. So the model architectures we used are, as I told you, EfficientNet B0 with CBAM and EfficientNet B3 with different data augmentation techniques. These are the uh, base model which we have used and the number of parameters for each, as I mentioned earlier, like EfficientNet B0 has 4 million parameters, whereas EfficientNet B3 has 12.2 million parameters. And the corresponding learning rate for Adam optimizer and what are the uh, models, blocks, all are mentioned on this slide. My teammate Manish will continue the presentation.
Greetings everyone, myself Manish Nadella and I'll be continuing with this presentation. So let's start this with a discussion about the model architectures which have been used. So we implemented two separate model architectures. One is efficient at B0 and the other is efficient at B3. So in general, EfficientNet it comes from a family of convolution neural network based architecture models. So this model can achieve higher accuracies with very less parameters using compound scaling. So EfficientNet usually scales depth, width, and input resolution together instead of tuning them independently. Uh, so for efficient at B0, in order to improve the accuracy, we have used a convolution block attention module, so or CBAM. CBAM usually enhances feature learning by applying channel and spatial attention. So channel attention usually focuses on the features which are important, and spatial attention focuses where these important facial regions are located in the given input image. So this particular modules combined together with that is efficient B0 and CBAM, they can help in improving the facial expression recognition because facial expressions have very subtle regions like eyes and mouth, which carry very strong emotional cues, and these modules combined together can help in identifying such subtle regions. So as explained, efficient B0 is our base model, and there is a CBAM block, which CBAM attention block, which is added to this base model. So we train these together with with ADAM optimizer with a learning rate of 1 e power minus 4 and label smoothing, which is which parameter is set to 0.1, and we have data augmentation and data generalization, which are the usual techniques to train these models. So this is the efficient at B0 module. Now coming to efficient at B3, this is a much larger and a more capable model variant. So efficient B3 is larger in size compared to the efficient B0, and it uses higher resolution images. So due to this, this model will be able to capture much wider much wider range of features from a given for the given image. So in our case, this model will be able to capture the facial expressions or the facial cues in much detail. Because of this, the number of trainable parameters will be more compared to B0, and also the resources required and train time will also be more compared to the efficient B0 module. So these were the two models which we have used for our training and comparison. So let's move on. Coming to results. So we have trained both these models using the FER 2013 dataset. So this dataset has around 35,000 grayscale facial images, uh, and these images span across seven different classes, that is seven different emotions. These emotions are very basic emotions like anger, happiness, sad, neutral, disgust, sad, and fear. So these 35,000 images are spanned across these seven different classes. And for 2013 is the standard benchmark dataset, which is used for the task of facial emotion recognition. Hence, we used the same dataset to train both our models. So, on training our model with the on training our models with this particular data set, we have achieved a validation accuracy of 68% for efficient at B0 and 71% for efficient at B3, which is as shown. The main difference clearly lies in validation accuracy, but it also lies in the inference time which is taken. So, as explained earlier, efficient B0 is a smaller model compared to B3. Hence, it takes very less time for inference compared to the efficient B3, whereas efficient B3 being a much larger model, a much deeper model, it takes significantly more time than the B0 model. And also, as explained earlier, the number of parameters which needs to be trained are very much higher for B3 than B0. So clearly there is a trade-off between the inference time and validation accuracy. So if we need a much faster model with a reasonable amount of accuracy, we can use efficient B0. Whereas if we need a more accurate model with a sufficient inference time, we can use efficient at B3. So we have a graph here, a training versus validation accuracy graph. So this is the graph for efficient and B3 model. So if you can see here, there is a significant drop. The graph shows a significant drop. So this drop occurs due to our two-stage training process. So while training the model while training both the models with FAR 2013 dataset, we have used a two-stage training approach. So in stage one, we freeze the trainable layers first, and we train the base model, that is the base efficient at B0 and the base efficient at B3 models on the FAR 2013 dataset. So so everything before the drop here is the stage one training, and everything after the drop is stage two training, where we unfreeze the layers and perform fine tuning on the model. So hence there is a drop in the graph, and also we can clearly see that the validation accuracy and the training accuracy are always close to each other. Hence, we can clearly say that the model has generalized properly rather than overfit. So these were our results for both the models. Now, apart from these two models, that is efficient at B0 and efficient at B3, which are trained using for 2013, we have also experimented with a different approach. That is, we have also experimented with using for 2013 and EffectNet model combined. Uh, and we trained an efficient at B0 model with this. So this particular model didn't perform as we expected. That is, the validation accuracy for this particular model is very less, which was close to 58%. Hence we did not include uh, that particular model setting in this slide. So the reason why there is a huge difference in accuracy, that is 58% for that particular setting, is because the combination of the for 2013 and the EffectNet dataset. So for 2013 is a low resolution grayscale, contains low resolution grayscale images, whereas EffectNet has a very high resolution RGB images. So this is one major difference in both the datasets. Hence, when we combine these datasets and use the combined dataset to train an efficient model or any other model, the model tries to generalize for each dataset individually rather than generalizing for the emotional features within the images. So, which means the model tries to learn the features in for 2013 separately and the features in EffectNet model separately, which is not ideal for this kind of emotion recognition task. Hence, there is a very huge difference in the accuracies for that model compared to these two models which are shown here. Uh, so that is about our model architectures and the results which we have obtained. So moving on, we have the line demonstration. So we have trained these models, and we have used the efficient B3, the weights of efficient B3 model to uh, integrate with our front end UI. So for the front end UI, we have implemented a very simple Flask based UI. So let's quickly go to that. So this is our app.py, which is a simple Flask application. And now let's run this. So running this launches our UI, so which basically has two modules. I'll be explaining them in more detail once the UI opens up. So yeah, here it is. So let's go. So now this is our front-end UI. Okay, that, yeah. So our UI module has two phases, uh, two modules. One is the emotion detection module on the left-hand side, and the other is the music recommendation table on the right-hand side. So yeah, so on the left hand side, we have the emotion recognition module. So this particular module tries to detect the emotion of the user in live, and then on the right hand side, based on the emotion detected, it tries to uh, pull the song recommendations from our database, which we our preset database, and that table is shown on the right hand side. So yeah. So this particular module on the left hand side, that is the emotion detector module, tries to detect an emotion for every 5 seconds and logs that particular emotion for every 10 seconds. This has been explained in detail in our demo video. So we have a demo video where we explain in detail each of these components and how they work, and also show the demonstration. So yeah, this is our front-end UI. Now let's go back to the presentation. So yeah, overall that is our front-end UI where we have our emotion detector module and our song recommendations. And based on the emotion detector module, the song recommendations will be pulled up from our preset database. So moving on, there are some complexities for this real-time emotion detection. So one major complexity can be the lighting conditions. So a, a user will not always be in very optimal lighting condition regions. So that is one very high and important complexity for us, because the lighting in the environment can always affect how the model performs, or how the model tries to capture the facial expressions. And also there are very diverse facial expressions for any given user. So it's not it is not always the case that every user will have the same set of emotions, or every user will have the same set of facial expressions when he's showing a particular emotion. So uh, so the happy face of one user will not always be the happy face of the other user. So there is always a variation in this facial expressions. Hence, that is also one of the complexities. And the third complexity is real-time processing. So as explained earlier, we have two different modules. One module which focuses on speed, and the other module which focuses on accuracy. So there is always a trade-off between speed and accuracy. That is, if you want much faster modules, there will be a drawback of accuracy, and if you want much accurate modules, there will always be a drawback of speed. So these are few complexities which we have come across when we are building this real-time emotion detection module for music recommendation. Now, moving on, we have our future works. So, for the future works, we can from the emotion detection point of view, we can try to implement a much deeper network architectures, or we can try to uh, fine tune the combination data set which I have discussed earlier, that is the combination of 2013 and EffectNet. We can fine tune this data set to our requirements, and we can train much deeper networks uh, which can improve the validation accuracy. And from the US point of view, that is the from front end point of view, we can implement multimodal emotion recognition, where we not only try to capture facial expressions, we can also try to capture the voice tone of the user, and also the body languages like the posture, the sitting posture or the standing posture, and uh, along with the voice tone can improve the emotion detection. And also we can try to bring in personalized recommendation, that is instead of using a preset database, we can use user feedback loops, or we can use user listening history in order to recommend songs in live instead of pulling them from the preset database. And we can also use mobile app development. That is, we can also integrate our module with uh, any other open source streaming services like Spotify, and we can integrate with them and develop a mobile app. So these are some of the future directions uh, we can take this project to. So coming to conclusion, so summing up everything, we have trained two different model architectures, that is efficient at B3 and efficient at B0 with convolution block attention module. So efficient at B3 performed better compared to the other network architecture. So the validation accuracy for efficient at B3 is 71.6%. But the inference time for the efficient B0 was just 15.2 milliseconds. So there's always a trade-off between the speed and accuracy. And we were able to successfully implement our front-end application for music recommendation using this particular model for emotion recognition. And we have also tried to explore other network architectures, that is the combined dataset with efficient B0, which I explained earlier, but that particular framework didn't work well because of the drawbacks with the combined dataset. So yeah, to sum up, we were able to successfully implement the uh, front-end application for music recommendation with emotion recognition module. And yeah, that is uh, the conclusion for our presentation. Thank you.